In this episode, we're finally putting everything together. Throughout this series, we've learned pods, deployments, services, ConfigMaps, secrets, persistent storage, Ingress, and Helm. Today, we'll use all of those concepts to deploy a real application on Kubernetes. This application includes a React frontend, a Node.js backend API, and a PostgreSQL database. By the end of this episode, users will be able to create, list, and delete records through a web interface running entirely on Kubernetes. Before deploying anything to Kubernetes, we first need to understand the application. We have a React frontend that users interact with. We have a Node.js backend that exposes REST APIs, and we have a PostgreSQL database where the data is stored. We already validated that the application works locally by creating, listing, and deleting users. Now our goal is to move this exact application into Kubernetes. Let's quickly review the source code. The front-end folder contains our React application. The backend folder contains our Express API and PostgreSQL integration, and the K8s folder will contain all Kubernetes manifests we'll create during this episode. This is a common structure you'll find in many real-world projects. Let's start from scratch. The first thing we'll do is create a workspace for this project. Then we'll clone the application source code from GitHub, and finally we'll create the Kubernetes folder structure we'll use throughout this episode. This folder will contain everything related to our Kubernetes deployment: the application source code, the Kubernetes manifests, and all configuration files required to deploy the application. Inside the repository, we have two main components: the front-end React application and the backend Node.js API. Later in this episode, we'll deploy both components to Kubernetes. Before creating any Kubernetes resources, I like to organize the project structure. ConfigMaps will store application configuration. Secrets will store sensitive values. PostgreSQL will have its own manifest. The front-end and back-end will have separate deployments and services. And finally, we'll expose the application using an Ingress resource. Let's understand how the application works before deploying it. The browser talks to the React frontend. The frontend sends requests to the backend API. The backend communicates with PostgreSQL, and PostgreSQL stores the data on persistent storage. Because the database is the foundation of the application, we'll start our Kubernetes deployment from the database layer. Before deploying PostgreSQL, we need to solve a very important problem. Containers are ephemeral. If a PostgreSQL pod is deleted and recreated, all the data stored inside the container would be lost. To avoid that, Kubernetes provides persistent volumes and persistent volume claims. Our database will store user information, so persistence is mandatory. This PVC is requesting 1 GB of storage. Kubernetes will automatically bind this request to a persistent volume. The PostgreSQL pod will later mount this storage and use it to persist data. At this point, we only created storage. We don't have PostgreSQL yet. Think of this as reserving a hard drive before installing a database. The backend depends on PostgreSQL. That means the database must exist before the backend starts. This is why we're deploying the infrastructure from the bottom up. We already solved the storage requirement using a persistent volume claim. Now let's solve the credentials requirement. PostgreSQL needs a username, a password, and a database name. We could hard code these values inside our deployment manifest, but that would be a bad practice. Instead, Kubernetes provides secrets. Think of a secret as a secure container for sensitive information. Instead of exposing passwords directly inside our deployment, Kubernetes stores them separately. Later, the PostgreSQL container will read these values from the secret automatically. Notice that we are not hard-coding credentials inside the deployment. Instead, Kubernetes will inject these values into the PostgreSQL container. We're creating a Kubernetes secret resource. This is the name our deployment will reference later. Opaque is the most common secret type and stores arbitrary key value pairs. Here we define the actual values. These are environment variables that the PostgreSQL container already understands. Now we have 2 building blocks ready. First, storage through a persistent volume claim. Second, credentials through a secret. In the next step, we'll finally deploy PostgreSQL and connect everything together. Now we're ready to deploy PostgreSQL. Notice that we're not starting from scratch. We already prepared storage using a persistent volume claim, and we already prepared credentials using a secret. The PostgreSQL deployment will now consume both resources. We're using a deployment because Kubernetes will manage the PostgreSQL pod for us. If the pod crashes, Kubernetes will automatically recreate it. Databases are usually deployed with a single writer instance. That's why we're starting with one replica. We're using the official PostgreSQL image from Docker Hub. PostgreSQL listens on port 5432 by default. This is where the secret becomes useful. Kubernetes will inject the values stored inside Postgres-secret as environment variables. PostgreSQL will automatically read those variables when it starts. This section tells Kubernetes where PostgreSQL should store its data. This is the default PostgreSQL data directory inside the container. Every table, every row, and every record will be stored here. This line connects the pod to the persistent volume claim we created earlier. Without this connection, the database would lose all data when the pod is recreated. Before creating the PostgreSQL deployment, let's visualize how these Kubernetes resources work together. On the right side, we have our secret. The secret stores the PostgreSQL credentials. The deployment references that secret using a secret ref. Kubernetes injects those values as environment variables into the container. On the other side, we have our persistent volume claim. The deployment references the PVC using claim name. Kubernetes mounts that storage inside the PostgreSQL container at the PostgreSQL data directory. This means the pod doesn't live in isolation. It consumes credentials from the secret and storage from the PVC. That's one of the most important Kubernetes concepts. Resources are small building blocks that connect together. Let's deploy PostgreSQL and see Kubernetes create our first database pod. We can see Kubernetes creating the pod. Once the status changes to running, PostgreSQL will be ready inside the cluster. Notice how Kubernetes attached both resources. The secret provides credentials. The PVC provides storage, and together they allow PostgreSQL to run correctly inside the cluster. At this point, PostgreSQL is running. However, pods are temporary. If this pod is deleted and recreated, its IP address will change. That means other applications cannot reliably connect directly to a pod. To solve this problem, Kubernetes provides services. A service gives our application a stable network identity. We're creating a Kubernetes service. Its job is to provide stable networking for our database. This name becomes extremely important. Other applications will use this DNS name to connect to PostgreSQL. Remember the label we added to the PostgreSQL pod? This selector tells Kubernetes which pods belong to this service. The label and selector must match. This is the service port. This is the port inside the PostgreSQL container. Cluster IP means this service is only accessible from inside the Kubernetes cluster. That's exactly what we want. Users should never connect directly to the database. Only the backend API should communicate with PostgreSQL. Notice that applications connect to the service, not directly to the pod. Let's deploy PostgreSQL service. Kubernetes automatically discovered the PostgreSQL pod through labels and attached it to the service. From this moment on, any application inside the cluster can reach PostgreSQL using the DNS name, Postgres-service. Now that PostgreSQL has storage, credentials, and networking, we can finally start building the backend API that will consume this database. At this point, our database is running inside Kubernetes. It has persistent storage, it has credentials, and it has a service that provides stable networking. Now we can deploy the backend API that will consume the database. The backend requires configuration values. Things like the application port and runtime environment are not sensitive. These values belong in a config map. Config maps allow us to separate configuration from application code. The backend also requires sensitive information. For example, database credentials. Instead of storing those values inside our source code, Kubernetes injects them through secrets. This deployment runs our Express API. Kubernetes will create pods from this template and keep them healthy. If a pod crashes, Kubernetes automatically creates a replacement. Notice what's happening. The backend receives configuration from the config map. It receives credentials from the secret, and it connects to PostgreSQL through a Kubernetes service. The backend does not connect directly to a pod. It connects to Postgres-service. Kubernetes DNS automatically resolves that service name to the correct pod. This means that even if PostgreSQL is recreated and receives a different IP address, the backend continues working without any changes. Let's build this step by step. First, we'll create the config map, then the secret, then the backend deployment. Finally, we'll create a service so the front end can reach the API. Our backend needs configuration values. These values are not secrets. They're simply application settings. Kubernetes config maps allow us to store those settings outside the application code. This makes our deployments more flexible and easier to maintain across environments. Our backend needs to know how to reach PostgreSQL. Notice that we're not using an IP address. We're using the Kubernetes service name, Postgres-service. Kubernetes automatically provides internal DNS resolution. This means our backend can always find PostgreSQL even if the database pod changes its IP address. This is one of the biggest advantages of using services in Kubernetes. Let's break this connection string down. The username is Postgres, the password is Postgres, the host is Postgres-service, the port is 5432, and the database name is Postgres. The most important part here is the host name. Instead of an IP address, we're using a Kubernetes service. Now we have everything the backend needs. We have application configuration stored in a config map. We have database connectivity stored in a secret. And we already have a running PostgreSQL database. The next step is to deploy the Express API and connect all these pieces together. This deployment will run our Express API. Notice that we're not hard-coding configuration values or database credentials. Kubernetes will inject those values from the config map and secret we created earlier. This keeps our application portable and environment independent. This line connects the backend to the config map. Kubernetes automatically injects the port and node_env variables into the container. The backend doesn't know where PostgreSQL is running. It only knows the service name. Kubernetes handles all service discovery automatically. Now that we understand how Kubernetes service discovery works, let's go back to our deployment. The backend doesn't need to know pod IP addresses. It only needs the service name. Kubernetes takes care of the networking for us. So let's continue building our backend deployment. Wait a minute. We're telling Kubernetes to run a container image, but where does that image come from? Up until now, we've been working with source code. Kubernetes cannot deploy source code directly. It deploys container images. So before applying this deployment, let's build our backend image and publish it to Docker Hub. This Docker file contains the instructions required to package our application into a container image. Kubernetes will later use this image to create pods. Docker is now packaging our Node.js application together with all dependencies into a portable container image. Before publishing the image, we need to authenticate with Docker Hub. Now we're uploading the image to Docker Hub. Once the image is available in a registry, Kubernetes can download and run it from any cluster. Now, this line makes sense. Kubernetes will pull this image directly from Docker Hub and use it to create our backend pods. Kubernetes is now creating the backend pod. During startup, it loads configuration from the config map. It loads the database connection string from the secret, and it connects to PostgreSQL using the Postgres service DNS name. One of the first things I always verify after a deployment is the application logs. The logs confirm whether the application started successfully and whether it was able to reach the database. At this point, our backend is running. It can communicate with PostgreSQL. It has access to configuration. It has access to secrets. But there is still one problem. Other applications inside the cluster don't have a stable way to reach the backend. To solve that, we're going to create a Kubernetes service for the API. Our backend is now running inside Kubernetes, but just like PostgreSQL, pods are ephemeral. Their IP addresses can change at any time. To provide stable networking, we create a Kubernetes service. Other applications inside the cluster will use this service name to reach the API. Before applying the service, notice this line. This selector must match the label defined in the deployment. This is how Kubernetes connects the service to the pods. If these values don't match, the service won't know where to send traffic. Let's take a step back and look at the architecture we've built so far. The front end will send requests to the backend service. The backend service routes traffic to our backend pods. The backend pods communicate with PostgreSQL through the Postgres service. PostgreSQL stores the data inside a persistent volume claim. Every layer has a specific responsibility. Services provide networking, pods run the applications, and the PVC guarantees data persistence. At this point, our database and API are already running inside Kubernetes. The only missing piece is the user interface. Our backend is now running and connected to PostgreSQL. The last application component we need is the front end. Just like before, we'll create a deployment for our React application. This deployment is much simpler than the backend. The front end doesn't need database credentials, it doesn't need a config map, and it doesn't communicate directly with PostgreSQL. Its only responsibility is serving the user interface. Kubernetes will pull the image from Docker Hub and create the front-end pod for us. Just like we did with the backend, we now need a container image for the front end. Kubernetes doesn't deploy React source code directly. It deploys container images, so let's build the image and publish it to Docker Hub. Now, the front-end image is available in Docker Hub. Kubernetes can pull it and create our front-end pods. Let's finish the deployment and deploy the application. Let's deploy the front end and see what happens. The deployment was created successfully. Something doesn't look right. The front end pod is showing an error status. Whenever a pod fails to start, the first thing we should do is check the logs. And here we can see the problem. The front end is trying to connect to a host called backend. But if we think about the architecture we've built, there is no Kubernetes service called backend. The service we created is called backend-service. So the front end is using the wrong host name. Let's fix the nginx configuration. Instead of backend:5001, now that we've updated the source code, Kubernetes won't see the change automatically. We need to rebuild the container image and publish the new version to Docker Hub. Now we need Kubernetes to pull the updated image. Let's restart the deployment and check the pods again. Perfect. The front-end pod is now running successfully. This is a very common troubleshooting workflow in Kubernetes. Check the pod status, read the logs, identify the root cause, fix the application, build a new image, push it to the registry, and redeploy. Just like PostgreSQL in the backend, the front-end pods need stable networking. This service will route traffic to our front-end pods. Notice that the selector matches the front-end label defined in the deployment. Let's take a look at the complete architecture we've built. The front end is exposed through the front-end service. Requests are sent to the front-end pod where our React application is running. When the front end needs data, it communicates with the backend service. The backend service routes traffic to the backend pod running our Express API. The backend then connects to PostgreSQL through the Postgres-service. Finally, PostgreSQL stores all application data inside a persistent volume claim, ensuring the data survives pod restarts. At this point, every component of our application is running inside Kubernetes. We have networking, we have storage, we have services, we have deployments, and the entire application is communicating correctly. However, there is still one problem. All of these services are cluster IP services. That means they are only accessible from inside the Kubernetes cluster. If we open a browser right now, we still can't access the application. So we need one final component, we need an ingress. The ingress will act as the entry point to our application and route traffic from the browser to the front-end service. Once we create the ingress, we'll be able to access the entire application through a friendly URL and complete our deployment. Let's create our ingress and expose the application to the outside world. Now let's create the actual ingress resource. The configuration is very simple. We'll define a host name. We'll define the route, and we'll tell Kubernetes which service should receive the traffic. In our case, every request will be forwarded to the front-end service. This is the URL we'll use to access the application. In production, this would be a real domain name. For our local lab, we're using students-portal.local. The ingress receives browser traffic and forwards it to the front-end service. From there, Kubernetes routes the request to the front-end pod. Our ingress resource has now been created. Let's verify that Kubernetes registered it correctly. We should see the host name we configured and the ingress class handling the traffic. Let's take one final look at the complete architecture. A user accesses the application through the browser. The request reaches the ingress, which acts as the entry point to the cluster. The ingress forwards the traffic to the front-end service. The front-end service routes requests to the React application running inside the front-end pod. When the front-end needs data, it communicates with the back-end service. The back-end service forwards requests to the Express API running in the back-end pod. Finally, the back-end stores and retrieves data from PostgreSQL through the Postgres service. PostgreSQL persists all data using a persistent volume claim. This architecture includes the core Kubernetes building blocks used in real-world applications, deployments, services, ConfigMaps, secrets, persistent volumes, and Ingress. Everything is now running inside Kubernetes. Let's test the application and see it working end to end. Before testing the application, we need one final local configuration. Our ingress is configured to respond to the hostname students-portal.local. Since this domain doesn't exist publicly, we need to tell our laptop where to find it. We can do that by updating the host file and pointing the hostname to the Minikube IP address. The request is hanging. We've actually seen this exact behavior before in the Ingress episode. This is a common issue on macOS when using Minikube with the Docker driver. The Ingress controller is running as a node port service and traffic isn't reaching it correctly. The fix is the same one we used previously. We'll change the Ingress controller service from node port to load balancer. After changing the service type, we need Minikube to provide the load balancer functionality locally. Now that the tunnel is active, we no longer need to point the hostname to the Minikube IP. We can simply point it to localhost. Let's try again. Perfect. The application is now reachable through the ingress. Let's test the complete application end to end. Now that everything is running, let's test the application. I'll open the browser and try to create a user. And it doesn't work. Let's investigate. The first thing I'll do is test the API directly. The API responds with an error. This is actually good news. It means the front end can reach the back end. The back end can reach PostgreSQL. But the database schema hasn't been created yet. Remember, this is a brand new PostgreSQL instance running inside Kubernetes. So let's connect to PostgreSQL and create the users table. Let's verify the existing tables. As expected, there are no tables yet. Now let's create the users table and verify it was created successfully. Perfect. Now let's check the contents. The table is empty, which is exactly what we expect. Now let's go back to the application and add a few users. Harry Potter, Hermione Granger, and Ron Weasley. Perfect. Now let's return to PostgreSQL and verify that the records were actually stored. And there they are. All 3 users have been inserted into the database. This confirms the complete application flow is working correctly. The browser is communicating with the front end is communicating with the back end, and the back end is storing data inside PostgreSQL running in Kubernetes. Everything is working correctly from the command line, but let's make the database interaction easier to visualize. Instead of using PSQL, I'll connect to PostgreSQL using dbeaver. To do that, I'm using a Kubernetes port forward. Now dbeaver can connect directly to the PostgreSQL instance running inside the cluster. Let's open the users table. We can already see the 3 records we created through the application. Now let's return to the browser and delete one of the users. After refreshing dbeaver, we can immediately see that the record has disappeared from the database. This is a great way to visualize what's happening behind the scenes. The delete request travels through the Ingress, reaches the front end calls the backend API, the backend executes a delete statement in PostgreSQL, and the database updates instantly. This confirms that every layer of the application is working together successfully inside Kubernetes. At this point, we've validated the complete end-to-end flow of our application running on Kubernetes. Before we finish, let's quickly verify that our persistent volume is actually working. Remember, the whole purpose of a persistent volume is to keep data even if a pod is destroyed. Let's test that now. We just deleted the PostgreSQL pod. If our database were storing data only inside the container file system, all data would be lost. Let's see what Kubernetes does. Kubernetes automatically recreated the pod because the deployment still exists. The important question is, did we lose the data? The records are still there. Even though the pod was destroyed, the data survived. That's because PostgreSQL is using a persistent volume claim. The storage exists independently from the pod lifecycle. This is exactly what we need for stateful applications running on Kubernetes. Let's quickly review what we accomplished. We deployed PostgreSQL with persistent storage. We deployed a Node.js backend using ConfigMaps and secrets. We deployed a React frontend. We exposed the application through an Ingress. We troubleshooted real issues along the way. We validated connectivity between every component. We created and deleted users through the application. And finally, we proved that our data survives pod restarts thanks to persistent volumes. That's a complete end-to-end Kubernetes deployment. Now that you've seen every Kubernetes building block individually, let's look at how the industry usually deploys applications at scale. Earlier in this episode, we manually created deployments, services, ConfigMaps, secrets, persistent storage, and Ingress resources. Understanding those pieces is essential. But once you understand them, you don't want to recreate everything manually every time. That's where Helm comes in. Let's take a quick look. Instead of talking about Helm, let's use it. Earlier in this episode, we spent quite a bit of time creating Kubernetes resources one by one. We wrote YAML files, we created deployments, services, secrets, persistent storage, and an Ingress. Now let's see what happens when Helm does that work for us. This is the exact same idea. We still need a front end, we still need a database, we still need services, secrets, and persistent storage. The difference is that Helm packages everything into a reusable chart. Let's deploy a complete WordPress application and see how much infrastructure gets created with a single command. Before we continue, let's clean up the resources from the Students Portal application. The goal here is not to compare 2 different applications running in the same cluster. I want you to clearly see what Helm creates for us. So let's remove the resources we deployed manually and leave only the WordPress application installed by Helm. Once the cleanup is complete, we'll inspect the cluster and see exactly which Kubernetes resources Helm generated automatically. Perfect. Now, the cluster contains only the resources created by Helm. Let's take a look and see what was deployed with a single command. Watch closely. We are not creating deployments manually. We are not creating services manually. We are not creating secrets manually. Helm is generating all those resources for us. Helm keeps track of everything it installs through releases. In this case, our release is called WordPress. That means Helm knows which resources belong to this application and can manage them as a single unit. Helm also gives us information about the application, its status, and useful commands for accessing it. Notice that Helm automatically generated a secure password and stored it inside a Kubernetes secret. We didn't have to create the secret manually. Helm not only deploys the application, it also creates and manages the credentials required by the application. Earlier in this episode, we manually created Kubernetes secrets. Here, Helm generated them automatically for us. Let's retrieve the WordPress username and password directly from the Kubernetes secret created during the installation. Perfect. We now have the application URL and the administrator credentials generated automatically by Helm. Let's log into WordPress. Notice that we didn't manually create a database. We didn't manually create secrets. We didn't manually create persistent volumes. Helm handled all of that for us. After logging in, we can access the WordPress administration panel just like we would in a real production environment. Let's make a simple change to verify that everything is working correctly. I'll edit the home page and update the title. Then I'll save the changes and open the website again. And there it is. Our changes are immediately reflected in the application. Think about what happened here. With a single Helm command, we deployed a WordPress application, a MariaDB database, secrets, persistent storage, services, and all the Kubernetes resources required to connect everything together. Earlier in this episode, we spent time building and understanding those components individually. Now you can see why that knowledge matters. Because when Helm creates these resources automatically, you already understand exactly what's happening behind the scenes. Helm keeps track of every resource that belongs to a release. Because of that, removing an application is just as easy as installing it. With a single command, Helm is now removing the WordPress release and all the Kubernetes resources associated with it. Notice what's happening. The WordPress deployment is being removed, the pods are terminating, the services are being deleted, and Helm is cleaning up everything it created. Just a few moments ago, we had a complete application stack running inside Kubernetes. Now the entire release has been removed. That's one of the reasons Helm is so popular in real-world environments. It provides a consistent way to install, upgrade, and remove applications. Before we finish, let's take one final look at everything we've accomplished throughout this Kubernetes journey. In this episode, we deployed our first real-world application on Kubernetes. We worked with deployments, services, ConfigMaps, secrets, persistent storage, and Ingress. We performed real troubleshooting. We validated connectivity between every component. We proved that our data survives pod restarts thanks to persistent volumes. And we saw how Helm can package all those resources into a single reusable deployment. Most importantly, we moved beyond simple demos and deployed complete applications running inside a Kubernetes cluster. If you'd like to build this project yourself, all the source code, manifests, and examples will be available on GitHub. You can find everything here, github.com/deleta/devops-basics-students-portal, and we're not done yet. In the next episode, we'll focus on Kubernetes best practices. We'll learn how to configure resource limits, implement health checks, improve security, use labels effectively, and work with liveness and readiness probes. These are the practices that help transform a working Kubernetes deployment into a production-ready Kubernetes deployment. Thanks for watching, and I'll see you in episode 14.